Hey guys, Mr. Backerberg here. In this video, we're going to look at optimization examples from mathematics.
So the first couple examples that we're going to do are just purely mathematical. So in this first one, we want to find two numbers whose sum is 20, and we want to maximize the product. We want the product to be as large as possible. So let's talk about what these two numbers are going to be. We can control the size of the first number. So I'm just going to let x represent that first number. Now we know that these numbers have to add up to 20. So the other number is going to have to be 20 minus whatever we choose to be that first number. Now really what we're trying to find is a product. So we're going to take these two numbers that we just came up with and we're going to multiply them together. So that's going to be x times 20 minus x. And this is going to be the function that we're going to try to maximize. Now, if I distribute that x in and maybe do a little rearranging, this is going to say negative x squared plus 20x. Now, when we're looking for maximum or minimum values, we're going to look at the first derivative of our function. So if I find the derivative of this function, using the power rule, drop the 2 down as a multiplier. So that'll be negative 2x. And then on the back end, it'll be plus 20. And then to find our critical numbers, I'm going to take this derivative and set it equal to 0. So negative 2x plus 20 equals 0. Subtract the 20 over, so we get negative 2x equals negative 20. Divide the negative 2 over, so we get x equals 10. So this is going to be our critical number. If we were to make a sign chart with this 10, plug in something to the left of 10 into our derivative. So say we plug in 9, plug that into the derivative, and we get negative 18 plus 20. So this is a positive interval. Plug in something to the right of 10, so maybe we choose 11. This would be negative 22 plus 20. So that would be a negative interval. So what we can see happening is to the left of this critical number, our function is positive or increasing. And to the right of this critical number, our function is decreasing. So because we were increasing and then decreasing, we found a maximum point on this graph. So that value of 10 is going to be the maximum x value that we can have. So then, if x is 10, then that other number also has to be 10. Now in this example, we're going to look at inscribing a rectangle. And what we're going to do is inscribe a rectangle under one arch of the sine curve. We want to figure out the largest area that the rectangle could have and what dimensions are going to give us that area. So let's talk a little bit about a sine wave, and I'm going to do a quick sketch of a graph for a sine wave between 0 and 2 pi. If we think about our unit circle, it takes 2 pi to make one full trip around the unit circle. So our sine wave is going to look something like this. Now we said we wanted to look at just one arch of our sine curve, so I'm actually going to erase part of this and just look specifically between 0 and pi. And what we're trying to do is inscribe a rectangle underneath this sine wave, and then we're going to maximize its area. Now one thing to point out is that these top corners of our rectangle are going to fall directly on the sine curve. So let's talk about what those ordered pairs would look like. If we were to focus on just this point right here, that's going to be some general x value, and then the height, the y value of that, is going to be whatever the sine of that x value is, since this is a sine curve. Now because this distance from the start of our sine curve to the start of our rectangle, that's our x distance, if we were to come in from the other side, this x value right here is pi. So if this distance over here across the bottom is x, then this distance over here across the bottom also has to be x. And that's going to help us as we're finding the width of our rectangle. Because if this total width is pi, and we've got x on either side of our rectangle, then the width of our rectangle is going to be pi minus 2x. And then the height of our rectangle is just this y value of the sine of x. Now we know that the area of a rectangle is the length times the width. So as far as the height goes, we said that that was going to be just the sine of x And then the width of our rectangle was going to be that pi minus 2x. So this is going to be our area function that we're looking to maximize. Now, in order to actually build this rectangle, we can't go past the halfway point of this arc. So for an implied domain of this function, we're going to be working between 0 and pi over 2 for those x values. So those endpoints might be important, but we also want to find some critical numbers by looking at the derivative of this area function. Now, because there's multiplying happening in here, we have to do the product rule to help us find the derivative. So the sine of x is going to be my u value, and the pi minus 2x is going to be my v. So finding the derivative, we leave the u thing alone. So I'm going to leave the sine of x alone, and then attach the derivative of the v piece. So the pi is just a number. So when you differentiate a number, that just turns into 0. With the negative 2x, that's going to differentiate into negative 2. But then we want to add on, now leave the v thing the same, so pi minus 2x, but then we're going to attach the derivative of u, and the derivative of the sine of x is the cosine of x. Now to find the critical number, we would set this derivative equal to 0, but going through and trying to do that algebraically is not going to be real easy for us to do. So this might be a case where it would be helpful to find a 0 graphically. So I'm going to take this derivative and type it into my calculator so that I can see the picture of its graph. So in my calculator, I have that derivative typed in. I'm going to do zoom 6, and we get this picture that we're looking at. Now remember, we said our domain was going to be x values between 0 and pi over 2. Now pi over 2 is a little bit more than 1.5, so we're looking between 0 and 1.5 for some place where this derivative is equal to 0. So I'm looking at this point right here where our derivative crosses through the x-axis. I'm going to go second calc, and I want to find that 0. So I'm going to arrow over close to that 0. First it asks me for a left bound point, so I'm going to go to the left of that 0, hit enter. Then it asks me for a right bound point, so I go past it, hit enter, enter, and it tells me that that x value is at about 0.71. So we just got ourselves an x value of about 0.71. Now technically we also want to look at these endpoints of our domain as well, and I'll show you why those will create problems as we go through and test to see which is going to give us a maximum area. So if we think about making this rectangle, then the height of our rectangle was going to be the sine of whatever x value we were working with, and the width of our rectangle was going to be pi minus 2x. And I'm going to talk about these endpoints first. If we've got an x value of 0, then the height of that rectangle, well, the sine of 0 is 0. And then if we do pi minus 2 times 0, that's going to be a width of pi. Well, multiplying those together to find the area, this would give us an area of 0. We're trying to maximize the area, so having an area of 0 isn't really a good thing. Now, as far as that x value of pi over 2, then if we find the height here, the sine of pi over 2 is 1, but then the width, if we do pi minus 2 times pi over 2, well, 2 times pi over 2 is pi, and then pi minus pi would give us a width of 0. So again, multiplying these together is going to give us an area of 0, which, again, if we're trying to maximize the area, 0 is not a good area. So then I'm focusing specifically on this x value of 0.71. Now the sine of 0.71 for the height of our rectangle, if we just go 2 decimals there, it's about 0.65 if we were to type that into our calculator. And then as far as the width of our rectangle, plugging in the 0.71 for the x there, pi minus 2 times 0.71, we get about 1.72 as that width. So these are going to be the dimensions of our rectangle, and if we multiply those together, then that's going to give us an area of about 1.12 square units, whatever we're using to measure this. That's going to be it for this video. Thanks for watching.